Welcome to Mindcast, the show where we explore the fascinating world of artificial intelligence and its implications for our future. I'm your host, Will, and today we're diving deep into one of the most pressing challenges facing large language models, the problem of hallucinations, and the cutting-edge techniques being developed to combat them. Now, when I say hallucinations in the context of AI, I'm not talking about psychedelic experiences. I'm talking about something far more subtle and potentially far more dangerous. Imagine you're having a conversation with ChatGPT or Claude, and you ask them about a recent legal case. The AI confidently cites specific court rulings, complete with case numbers and dates. Everything sounds perfectly legitimate. There's just one problem. Those cases never existed. The AI made them up, whole cloth, and presented them with the same confidence as if they were citing the Constitution. This isn't science fiction. It actually happened. In 2023, a lawyer submitted a legal brief written by ChatGPT that cited completely fabricated court cases, leading to significant professional consequences. And here's the thing that makes this so fascinating from a technical perspective. This isn't a bug in the system. It's not something that can be simply patched or fixed. Hallucinations are an inevitable consequence of how these models fundamentally work. To understand why, let's think about what these large language models actually are. Despite their impressive capabilities, LLMs are not knowledge repositories in the way humans think of knowledge. They don't have a mental filing cabinet where facts are stored and retrieved. Instead, they're essentially very sophisticated prediction engines. They've been trained on vast amounts of text with one primary objective: predict the next most likely word in a sequence. Think of it like this. If I start a sentence with, "The capital of France is," an LLM has learned that Paris is the statistically most likely next word based on patterns it's seen millions of times in its training data. But here's where it gets tricky. The model's training objective rewards it for generating text that's linguistically plausible and flows well, not necessarily for being factually correct. Factual accuracy is just one signal among many, and it's often a weaker signal than linguistic structure or common phrases. So, when faced with a query about something it has incomplete or conflicting information about, the model doesn't gracefully say, "I don't know." Instead, it makes its best statistical guess rendered with the same fluency and confidence as a factual statement. This reveals a critical trade-off. The very mechanism that enables creative writing and novel text generation is inextricably linked to the capacity to generate plausible falsehoods. Now, not all hallucinations are created equal. We can actually categorize them into several types. First, there are factual inaccuracies, the most common type. These range from subtle errors, like misattributing a quote, to fabricating entire events. Then we have nonsensical responses, where the model produces outputs that are grammatically correct, but logically incoherent. And perhaps most damaging are contradictions, where the model either contradicts information you've provided or contradicts itself within the same response. The danger of these errors is magnified in high-stakes domains like medicine, finance, and law. An AI's confident assertion of a falsehood, whether it's a drug interaction, a financial figure, or a legal precedent, can have catastrophic consequences. And here's what makes it particularly insidious: the model's tendency to reinforce incorrect assumptions and their complete lack of self-awareness about their own errors. So, how do we tackle this challenge? Researchers have developed several fascinating approaches, each operating on different principles. Let's start with one of the most popular, retrieval augmented generation, or RAG. The core idea here is elegant in its simplicity. Instead of relying solely on the model's potentially flawed internal memory, we ground it in external, verifiable knowledge sources. Here's how RAG works. When you ask a question, the system first searches through a knowledge base, like a vector database of documents, and retrieves the most relevant information. It then provides this information to the language model as additional context alongside your original question. This grounds the model's response in timely, domain-specific information, dramatically reducing the risk of fabricated answers. RAG has evolved significantly since its early days. We've moved from simple retrieve and read pipelines to sophisticated modular systems that can iterate, retrieving information, reading it, then retrieving more based on initial findings. The primary strength of RAG is its ability to handle new or rapidly changing information. Plus, it provides traceability since you can link generated text back to source documents. But RAG isn't perfect. It suffers from what researchers call the garbage in, garbage out problem. If your retrieved documents are irrelevant, biased, or factually incorrect, your AI's output will be similarly flawed. Even with relevant documents, the language model can still misinterpret context or struggle to synthesize conflicting information from multiple sources. Another major approach is fine-tuning, essentially reshaping the model itself by modifying its internal parameters. This includes techniques like reinforcement learning from human feedback, where humans rank different model outputs to teach the system what kinds of responses we prefer. There's also direct preference optimization, a more efficient alternative, and specialized techniques like hallucination-aware tuning, which explicitly teaches models to avoid specific types of factual errors. Fine-tuning can lead to significant improvements in domain-specific accuracy, embedding desired factual knowledge directly into the model's parameters. But here's where it gets really interesting and a bit scary. Research has shown that when you fine-tune a model on new facts that contradict its existing knowledge, it can actually increase hallucinations. The model struggles to integrate conflicting information, leading to instability and degraded factual reliability. It's like trying to teach someone a fact that contradicts everything they thought they knew. It creates cognitive dissonance. Then we have multi-agent debate systems, which represent a fascinating approach inspired by collective intelligence. The idea is to simulate a society of minds where multiple AI agents engage in structured debate. They propose answers, provide reasoning, critique each other's responses, and iteratively refine their conclusions over multiple rounds until they reach consensus. This approach has shown remarkable results on complex reasoning tasks. There are compelling examples where a debate between two models solved problems that neither could solve individually, but it's not without issues. These systems can fall prey to echo chamber effects, or what researchers call tyranny of the majority, where an initially popular but incorrect answer becomes entrenched and amplified by the group. Plus, the computational costs are substantial. Each round of debate requires multiple calls to the language models. Now, here's where things get really fascinating. All the methods I've discussed so far either rely on external data, modify the model's parameters, or require significant computational overhead. But what if I told you there's a third class of techniques that operates entirely on the model's internal state at the moment of generation, without any additional training or external knowledge? These are called inference time decoding strategies, and the most promising among them are layer-wise contrastive decoding methods. To understand these methods, we need to dive into the internal architecture of transformer models. Here's a key insight. Knowledge within these models isn't distributed uniformly across all layers. Instead, different layers specialize in processing different types of information, forming what researchers call a functional hierarchy. The early layers focus primarily on surface-level features, syntactic structures, part of speech tagging, basic linguistic patterns. Think of them as handling the noise and structural elements of language. They often show high uncertainty, with many possible next words seeming plausible. But as information flows through the network, the deeper layers progressively build more abstract, semantic representations. This is where factual knowledge is believed to be localized, refined, and integrated. Here's a classic example that really illustrates this phenomenon. Consider the prompt. The capital of Washington State is... In the early layers, Seattle might have a very high probability because it's a prominent city frequently associated with Washington in the training data. But as the model processes this through its deeper layers, the factual knowledge that Olympia is the correct capital gets injected, causing its probability to rise significantly, while Seattle's probability may remain stable or even decrease. This observable evolution of probabilities across layers is the key signal that contrastive decoding methods seek to exploit. The central principle is to amplify the factual signal that emerges in later layers by contrasting it against the more superficial, pattern-based predictions of earlier layers. It's like mathematically disentangling the critical factual information from accumulated linguistic noise. The first major breakthrough in this area was a technique called DOLA, decoding by contrasting layers. DOLA's approach is elegant in its simplicity. During generation of each token, it contrasts the probability distribution from the final mature layer with the distribution from a strategically chosen premature layer earlier in the network. The final probability of a token is then adjusted based on the difference between these two layers. The most critical design choice in DOLA is how it selects which early layer to use. Rather than using a fixed layer, DOLA employs a dynamic strategy based on something called Jensen-Shannon divergence, or JSD. For each token generation step, it calculates the JSD between multiple candidate early layers and the final layer, then selects the layer with the highest JSD as the premature layer for that specific decoding step. The intuition behind this is that a large change in probability distribution signals a point where the model has significantly updated its understanding, likely by incorporating crucial factual knowledge. By contrasting distributions from just before and after this major shift, DOLA aims to isolate and amplify the impact of that newly emerged knowledge. While DOLA showed significant improvements in factuality, researchers discovered a critical flaw in this design. Here's the paradoxical finding. Providing DOLA with more candidate layers to choose from actually decreased its performance. This is deeply counterintuitive. Standard optimization logic suggests that more options should lead to better or at least equal outcomes. This finding exposed a fundamental brittleness in DOLA's approach. The layer with the highest JSD isn't necessarily the best layer for improving factuality. A large divergence could represent crucial factual refinement, but it could equally represent a shift toward more complex but still incorrect reasoning, or simply amplification of noise. By committing to a single heuristically chosen layer, the entire process becomes highly sensitive and brittle. This is where SLED comes in. Self-Logit's evolution decoding. SLED represents a massive conceptual leap from DOLA's heuristic-based approach to a principled optimization framework. Instead of trying to pick the single, best layer, SLED embraces information from all of them through a sophisticated ensemble approach. Here's SLED's core insight. The evolution of information across layers can be treated as an approximation of the training process itself. The ultimate goal is to align the model's output distribution with the true but inaccessible real-world factuality distribution. During training, this alignment happens through backpropagation with ground truth labels. At inference time, SLED creates a robust estimate of this real-world distribution using information encoded across all the model's layers. SLED operates through a carefully designed three-phase process. In phase 1, it estimates what researchers call the latent knowledge distribution by analyzing how logits evolve from early layers to the final layer. For each early layer, SLED measures how well the observed evolution direction aligns with theoretical gradients that would arise if specific tokens were the correct answers. This produces individual votes from each layer on what the correct next token should be. Phase 2 is where SLED's robustness really shines. Instead of selecting a single layer like DOLA, it computes a weighted average of all the individual layer estimates. Layers that show clear, confident evolution toward particular tokens get more influence, while noisy or uncertain layers are downweighted. This ensembling approach smooths out noise and potential errors from any single suboptimal layer, resulting in a far more robust estimate of the model's collective latent knowledge. Finally, in phase 3, SLED performs what's essentially a single step of gradient descent. It computes the gradient of the divergence between its latent knowledge estimate and the final layer's distribution, then updates the output logics accordingly. There's a crucial hyperparameter called the evolution rate that controls the strength of this correction, allowing for a careful balance between the model's original trained output and the internal correction signal. Now, you might be wondering about computational overhead. Processing every layer sounds expensive, right? SLED addresses this brilliantly through something called the evolution scale parameter. This restricts the computationally intensive calculations to only the most probable tokens from the final layer's original distribution, dramatically reducing computational complexity while focusing corrective effort where it matters most. The results speak for themselves. Across a wide range of models, from Gemma to Mixtral to GPT variants, and scales from 1 billion to 45 billion parameters, SLED consistently and significantly outperforms both vanilla decoding and DOLA on factuality benchmarks. We're talking about improvements of 1 to 75% over DOLA in many cases, with some benchmarks showing even more dramatic gains. What's particularly impressive is SLED's consistency. While DOLA's performance can be erratic, particularly on certain benchmarks, SLED provides steady, substantial improvements across diverse models and tasks. This empirical success validates the theoretical advantages of its principled, optimization-based, ensemble-driven design over brittle heuristic approaches. But here's what really excites me about the future of this field. We're not going to rely on any single approach. The path forward lies in intelligent hybrid systems that dynamically combine these complementary techniques. Imagine a system that uses SLED as an internal confidence metric to decide when to invoke more costly RAG retrieval. If the internal correction signal is small, trust the model's parametric knowledge. If SLED reveals significant internal conflict, that's a trigger to ground the response in external documents. Or consider applying SLED to multi-agent debate systems. Instead of giving each agent equal voice, weight their contributions by their internal SLED consistency scores. Agents that are more certain, based on their layer-wise evolution, get more influence in the final consensus. This could help mitigate those problematic echo chamber effects we discussed earlier. Perhaps most intriguingly, the correction signal that SLED generates could become a training signal itself. Imagine fine-tuning models to minimize their internal divergence, essentially teaching them to be inherently more self-consistent across layers. This could lead to models that have learned the very process of introspection and self-correction that SLED simulates at inference time. As we wrap up today's deep dive, I want to emphasize that the challenge of hallucination isn't going away anytime soon. It's fundamentally rooted in how these probabilistic systems work. But what we're seeing with techniques like SLED is a maturation of the field, a move away from clever tricks toward robust, mathematically principled methods that actually work consistently across different models and tasks. The ultimate goal remains unchanged, developing AI systems that are not only fluent and creative, but also trustworthy and verifiably factual. We're not there yet, but advances like SLED show us that the vast repository of factual knowledge already exists within these models. We just need better ways to unlock it. The future likely lies in the intelligent synthesis of internal introspection, external grounding, and careful alignment. That's all for today's episode of Mindcast. I hope this exploration of LLM hallucinations and mitigation strategies has given you some insight into both the challenges and the remarkable progress being made in this field. As these techniques continue to evolve and combine in new ways, we're moving steadily toward AI systems we can truly trust with high-stakes decisions. Until next time, keep questioning, keep learning, and remember, even our most advanced AI systems are still learning to tell truth from statistical probability.